My name is Jose Gonzalez, and today I will talk to you guys about the overall level of quality of water in the Waikato River. This video is for my environmental and resource economics paper, in which Ricardo Scarpa is the lecturer. So hopefully you guys will be able to understand how, with a specific analysis of water quality in the Waikato River, we can both achieve an improvement in the condition of the water and also increase the amount of recreational uses. Now we will give a brief overview of how we are gonna structure this presentation. First of all, I'll give a brief introduction on the topic at hand. Secondly, we will explain, we'll give an explanation of the analysis of different variables relevant to the quality of water from a chemical and theoretical background. Thirdly, we shall explain which variables were chosen for our multiple regression model so we can state our regression equation as well, and we can explain the expected outcomes from this regression, of course, based on the variables that were chosen. Fourthly, we would present our summary output table in order to discuss the results, see if the findings were significant or not, or if were the ones that we expected. It is important to say that we will mention as well how we created our y variable, so our dependent variable, how we developed the index of quality of water, but we will explain this further on. Also, to address for multicollinearity, we'll run regression models, and also to find significant relationships between our explanatory variables. Lastly, we will suggest a policy solution, which we think that it could work in order to decrease the amount of nitrogen that's in the water at this point in time in the Waikato River, which it's a really big issue. So, in terms of the introduction, water quality has been affected directly or indirectly in the Waikato River in the past 20 to 30 years, let's say, and from a source and non-source contamination point. The difference between this direct and indirect pollution or contamination of the water is that the source ones are specifically in certain points, so they can be identifiable. You know which ones they are, such as paper mills or meatworks company, energy production companies, or waste or rubbish processing companies. They can be directly identified instead of the other ones, which cannot be, which are done from dairy farming and from livestock ownership or producing meat and those sort of things. That the urine from the cows and also from different types of livestock, they possess high levels of nitrogen, and these ones are being run off into the storm drains, which are of public use, of course, so you can't really identify who is contributing to the amount of nitrogen in the river highly or more than the other ones. So farmers are mainly here the ones that we are trying to deal with. And also, a study by the Regional Council say that 70% of nitrogen comes from no-source contamination points. The aim of this research is to analyze these contaminants, so different types of contaminants that have been affecting from no-source and source contamination, and try to adjust them accordingly with a policy solution after we've done the analysis and try to meet that target, which is to make it swimmable and fishable. Okay, so firstly what we did was an analysis of different variables relevant to water quality. This analysis was done from a theoretical and a chemical background, which means that we used a study from the Regional Council, over 20 years of data on all different variables that are important to quality of water. And we also try to identify how they correlate to one another and why practically do they affect the quality of water as well. So this study was done over yearly trend slopes, which means that how have they increased or decreased year to year, and also we were able to correlate them with one another because the results are for every single variable, such as temperature, total nitrogen, total phosphorus, chlorophyll, and ammonia, arsenium, so many other ones. With this insight, we will be able to expect to understand how these ones will be important for our model. In this variable analysis that we did, we found some really surprising results. First of all, temperature has risen yearly since 1992 on 0.4%, and dissolved oxygen decreased by 0.2. So we can see how they're correlated negatively, so saying one of them has risen, the other one has fallen. Why is this? Temperature, in higher temperatures, is a lot harder for trouts to live in, and the reason why is because trouts live in colder waters, and colder water possesses more dissolved oxygen than higher temperatures, according to several to Janssen, which is one of the studies that we looked at. He was talking about how these ones are really highly correlated in that way. Well, so we can see why one of them will go up and the other one will go down, drop, according to the study performed by the council as well. Turbidity and visual clarity are both correlated. Why is this? So if we have increasing turbidity, which is usually seen as the amount of mud and that we can, and also there is particles which will disallow an average human being to look through the water. So the water is turbid, so it's being mixed more, which is usually caused by a lot of rain and those sort of things. So visual clarity, of course, will drop if turbidity increases. Visual clarity means for human beings they won't be able to see as easy as they can. And also turbidity, because of these particles that are more condensed, it will be easier for the temperature to rise, because these absorbed particles absorb heat a lot easier. So high turbidity, more absorbed particles, high temperature, lower dissolved oxygen. So we can see how this is going. BOD5 shows correlation with dissolved oxygen. Why? Because it's the amount of organic material that is in the water, and if we have a higher amount of organic material, we'll have a higher amount of dissolved oxygen needed to process all this by the living creatures, such as different types of fish and also algae and different animals that live in the Waikato River. Arsenic levels have decreased from 0.8% to 1.3%, so we know that they have improved. We won't really look into much detail on this one, but arsenic, the higher amounts of arsenic that you could probably identify, they will be in taupo due to geothermal activity. From getting it, so the amount of dissolved oxygen will drop significantly, which is exactly what we saw as well, that it has dropped throughout the past 20 years. Also, more algae and plants will lead to higher turbidity in the water, which will then lead into probably higher temperatures. Ammonia has decreased due to lower contamination by paper mills and meat work factories, which is something that was mentioned in the study of the regional council as well. And throughout the past 20 years, it has decreased significantly. This is source contamination. Total phosphorus and chlorophyll, they both show significant improvements, which is really important. They have both dropped and in the past 20 years, so we won't really take them into consideration in an analysis because they are under control. Okay, so the variables chosen for our regression model are several of them, the ones that we mentioned. In order so we can determine the quality of water, we will have pH, which is the level of pH, in order so we know that the water is either drinkable or not. In general terms, pH will have to be ranging between 7.5 and 8. That will be a really good overall pH. So all these variables are important factors when analyzing the overall quality of the water, which is really important to mention, and also their relevance in the past 20 years makes them indispensable when calculating their impact on the water. Okay, so the way we want to explain our expected outcomes is that the quality of the water is going to be our y variable, right? So it's going to be our dependent variable, depends on how all the independent variables behave and how they increase or decrease. And in order to analyze them, we needed to know the theoretical and chemical background that we gave, because otherwise, why would they be relevant to the model if they don't really indicate something that's related with water quality? So the expected outcome is that a unit increase in xi, so xi can be any of our independent variables. These are the ones that we expect that are on the right hand side in the diagram. So a unit increase, we expect increasing pH, decreasing quality of water, increasing temperature, decreasing quality of water, increasing dissolved oxygen, increase in quality of water, because we know if there's more dissolved oxygen, there's going to be more living organisms in the water. Then increasing arsenic, decreasing quality of water, increasing total phosphorus, decreasing quality of water, increasing chlorophyll A, decreasing quality of water, increasing total nitrogen, decreasing quality of water, and then increase in biodegradable oxygen demand as well will be a decrease in quality of water. So these are the expected outcomes. We put them in this visual with this visual diagram that is probably more attractive to the eye, so people can actually understand what we mean by it. Okay, so in order for us to create the quality index, which is our y, our dependent variable, we based ourselves in the guidelines and standards set up by the regional council, which means that there is certain levels of each contaminant and each variable that they will be considered unsatisfactory, satisfactory, or excellent, in the case they are excellent, very few of them fall under this category. So we have here all the different parameters that we need to follow, right? So to create this quality index, we used the if and then logic test in Excel, and we were able to identify all across the sample, which is this sample, the sample data that was gathered from the study of the regional council that was performed, the more recent one, over that it was done over an entire year in every single month, and and the sample was taken at different source, different sample site, and what they did is that they calculated the different levels for the different contaminants and different chemicals and different variables, temperature and all that. So what we did is that we gave a level of quality for every sample point, for every data point. So let's say an example would be there was a sample taken in Taupo at 1st of March of 2011, and they took some from this sample. They analyzed the levels of pH, temperature, dissolved oxygen, turbidity, arsenic, ammonia, total phosphorus, chlorophyll, total nitrogen, and BOD5. What we did is that we gave each one of the results of the sampling. We gave it a quality level between 1, 2, and 3, depending on the parameters. We calculated this for every single sample point, and what we did after is that we calculated, and overall, in every sample taken, we calculated the average, and that's how we got our quality index, which is really important for our regression model and also for our further on analysis. The outcome of the quality index analysis, this is a bit of a statistical summary. The mean was 2.226, which means that it's overall the quality level of water is in a satisfactory category according to the parameters set by the regional council. So a significant improvement has actually been performed by the different authorities. Okay, so after we did this, we were able to give a variable to our y. We could regress all our independent variables with our dependent variable. It is important to say that the raw data was gathered from a report that it was used by the regional that it was published by the regional council in 2011 that analyzed the different levels of contaminants in the water in all across samples. This is the multiple regression output. This is the output that we got from running this multiple regression. What we found was really interesting because the signs of the different coefficients that we found at the end, they were all statistically relevant. So we can see the signs at the end of the probability that they are more than our t-value, which they are all less than, well, some of them 5%. The 3-star ones are the most statistically significant, which is below 1%. Yeah, so this we can see how the estimates and the signs of our coefficients, they are what we expected. So this estimate will be for temperature negative. We know that temperature rises, quality of water falls, which is what we expected in our regression model. Total nitrogen, the same thing. It goes for a rise in the nitrogen levels, makes quality of water fall. Same for, well, dissolved oxygen. We knew that they both had to move together. So if there was an increase in dissolved oxygen, increase in temperature, which is shown by the 0.035. Chlorophyll is a negative number, also just like arsenic. High turbidity as well. We created a dummy variable for this one, which is really important to mention because we ran the model first, and just with the turbidity level, we got no statistical significance on this. So we created a dummy variable, which was for all equals to 1, all the samples that were above 5 in the level of turbidity. For BOD5, for biodegradable oxygen demand, we got a negative coefficient, which is what we expected. For temperatures between October and May, we created a dummy variable because summer weather, so it's hotter, and yeah. The intercept was 2.8, which is really good overall. And the statistical coefficients, we see our multiple R square 0.88. That's a really good R square, which means our independent variables really explain our dependent variable. Then we got our multiple R square, which is adjusted R square, which is of 0.869, which is really good. So we know that our model is statistically significant after we've done the proper analysis. Quality of water as its variance from the mean is really small within the parameters and the guidelines that have been set. And in more theoretical terms, the variation of pH is not sufficient to explain how an increase in its level will affect the quality of water. The same thing will happen for total phosphorus and for ammonia. we're only omitting variables that are not relevant. Then single regression output, we would run single regressions between our independent variables to address for multi-correlation and also for to find a statistically significant relationships between our variables. What we found is that we only want to worry about two of them, which is the level of which is the single regression between turbidity and total nitrogen, which has a high R-square, same as the one between temperature and dissolved oxygen. So temperature being our dependent variable and dissolved oxygen are independent. We see a statistically significant result, 3 stars, same as the other one that we mentioned before. And we want to focus on this one because the other ones have a really low R-square, and we are not really going to target them with our policy solution that we want to suggest. The variables speak for the policy solutions. As we said, we mentioned that in our regression, the ones that were statistically significant in the single regressions were total nitrogen with turbidity, and also the other one was temperature and dissolved oxygen. So these are the variables that we want to analyze also as well, because in graph number 1 and 2 right here, we can see how between 2007 and 2011 they have increased, well, by this has been a small constant increase throughout the different sample sites. And also as well, for all three variables, we can see a negative impact in our multiple regression model, and also in our singular regressions we can see how they are both statistically significant. And if we run single regressions between themselves, between these independent variables, a potential decrease in any of these variables as well will have a huge impact in dissolved oxygen, which is what we want. We want higher dissolved oxygen for a higher level of to increase the amount of fish in the water and improve water quality. So specifics for policy implementation, what we have right here is that we want to increase the utility for users. So saying utility 1 equals to our beta, which is going to represent the change in utility with a change in total cost to accessing the site, which in this case we are going to keep it constant. We're not going to worry too much about total cost, because we know that getting to the Waikato River from different sites, it's for every single the Waikato River runs us throughout different towns and population and different cities, so we don't really want to focus on this. So we want to focus on the Q1, which is the quality indicator. So if we know that the quality indicator goes up, we expect utility to go up. Why? Because it's a feature that people value more. So if we have a cleaner river with less nitrogen, lower temperatures, even maybe more fish, will get more people interested in fishing, more people going to use it for swimming or for sports or for all sorts of other activities. So this is what we're trying to stick for. And also increase in quality of the river as well. The way this policy works is through the implementation of a tradable pollutant permit or a specific right that you hold to pollute, basically saying that these ones are tradable because they can trading in a new market, this hypothetical market that will be selling and buying pollutant rights for dairy farmers and meat works producers, and also different people and different businessmen and organizations that own livestock. The way we expect to achieve this is by charging them this pollutant, the price for this pollutant permit for single unit of pollution that you will need to buy in order for you to be able to keep your livestock and keep your production levels and keep the amount of cows that you have. We offer two solutions. One of them was through a measuring device that basically was put at the end of the drains and the different ways they have to channel water out of their property, and in that way you can measure the amount of nitrogen that is leaving the property, and you can determine how much you're polluting and charge them accordingly. Or the other way was to a per cow tax, so saying that per cow you hold, you're being charged a tax. But instead, because we were talking about trading permits, we will expect this tax to be implemented as a tradable unit of pollution. So saying you have 1 cow, I have 20 cows, I will buy 20 units of pollution of tradable pollutants, of this permit, and you can trade them. So saying if 1 cow dies, or if you are only going to be using 10 of them, or you are selling the other one, you can sell also the right to pollute. Like this, what we expect to achieve with this is to just hold a second, decrease the amount of nitrogen that will result in a chain reaction. What we mean by this is that because we're charging the direct directly the polluters and the major contributors to the contamination of the Waikato River in terms of nitrogen levels. We expect the nitrogen amounts to decrease because not everyone can afford it. Also, there will be that sort of negative externality that they're causing because of them producing meat or dairy product, which is on high level of nitrogen. We'll expect the nitrogen levels to decrease as well because there will be a higher government revenue in terms of the pollutant permits that they have to buy in order for them to be able to keep their productivity levels up and keeping their livestock within their property. So lower amount of nitrogen will lead to what we said before, higher amounts of dissolved oxygen for the living creatures and different animals that live in the water. Also, this will lead into also lower turbidity, and we know that lower turbidity is related with temperature. From the single regressions that we run, we can say that, for example, if total nitrogen is reduced by 1, we would expect a reduction of turbidity by 15. Which is really unlikely, of course. This is just like as a measurement, because total nitrogen is measured in really small units, so they wouldn't really ever get to 1, but it's just so we understand how they will be significantly and statistically proven that these ones will move, one will go up and the other one will go down, or the other way around, vice versa. Same for the amount of dissolved oxygen. So if we have a higher amount of dissolved oxygen, we will expect temperature to fall by minus 2.26 according to our single regression that we run. So it means that they are negatively correlated. One of them will go up, and the other one of them will go down. So as a conclusion, we can say we have explained and discussed the different components of water that contribute to the contamination of the river and that are really important between each other, and they have been also in the past 20 years. So not only to us, but to a regional council. We've established single and multiple regression models that they are both statistically significant in order to determine and to analyze quality of water and to adjust the main variables and target them. And so we know how much they will be changing if we were to reduce the amount of nitrogen in the river, or if we're going to increase the amount of dissolved oxygen. And with any other variable, it could be done as well, but we just focused on nitrogen this time. Then having a quantifiable measure for our dependent variable, which is really important because we gave it a quality feature. So saying that we're considering all the different contaminants, we gave a quality feature to the to water, which is really good. That was 2.226, which is overall quite good, satisfactory levels according to the parameter set. And the expected damages on quality of water, they were what we assumed that they will be. So, lastly, we proposed a policy solution that it will directly target the amount of nitrogen in the river. We will probably reduce it. We'll have more money in the budget, which at the end will be probably put back into society through different ways, but hopefully by improving the water quality, of course, because that's what the policy is for. As a chain reaction, affect temperature and turbidity, which is what we explained. By doing so, we will increase the overall quality of water and also increase the utility levels. So everyone's happy, the government's happy, people are happy. And the only people that will probably be negatively affected will be the farmers, but hopefully they will come around to understand and be environmentally sensitive about this topic. Thank you very much for listening to me today. I'm really grateful for all this, and I hope you guys have a good rest of the year of 2015.